Hi everyone, welcome to Mathematical Systems 2. In this lesson we're going to talk about more mathematical system properties. And the specific properties we're going to talk about are the commutative, associative, identity, and inverse properties. Now we're familiar with these properties from real numbers, and we know that they work with addition and multiplication. So we're going to use some real number examples as we go through this, but we're also going to use like the light switch example. We're going to use some examples like that in order to investigate each one of these four properties. So let's start with the commutative property. And if I am given a binary operation, and let's call our binary operation little circle, then the commutative property, if I have a set with any two elements A and B and I use the binary operation on them, then that is going to be equal to the binary operation on the elements B and A. So the commutative property is a how would you say, a place switching property or an order switching property. And that's kind of a way to remember it. The associative property, if I have three elements, then I'm going to have A operated with B operated with C, and we're going to operate B and C together first. And then that's going to be equal to A operated with B operated with C, but using grouping we're going to do parentheses, and we're going to do the operation on A and B first. So I like to call this a choosing or an order of operations property. In other words, which ones are you going to combine first before you combine the third one? Okay? The identity property says that there exists an element I such that, and this is the symbol for such that A operated with I equals I operated with A is equal to A. So in other words, the identity element preserves the identity of any other object element in the set. And then what's the inverse property? Well, the inverse property says that there exists an element B called the inverse of A such that A operated with B is equal to B operated with A is equal to the identity element. And so in this case, when you operate the objects together, you end up with the identity in the set. So now we're going to look at a few examples to try and flesh out these ideas. So what I have here is an operation, small circle standing for O operation, and a set with three elements A, B, and C. And then you can see the results of this set right in here. And what we want to do is we want to check to see if this is a commutative set. And also we want to ask ourselves maybe to show something like show that A operated on B is equal to B operated on A. Okay? So let's start by doing that. So here is A, here is B. So A operated on B is the element B. So I know that this is B, and then I do here's B, and then here's A. So B operated with A is also equal to B. And so I end up with B equals B. So I have shown that the elements, in this case I have shown A and B under this are commutative. So what I have done is I've shown that those two elements are commutative. How would I show that the whole set is commutative? Well, what I would have to do is check all combinations of every element. So let me give you an example of this. I'd have to check if A done with A is equal to A done with A. So right away I can see that these are all redundant. So if I do it with an element with itself, that's going to be obviously commutative. So then the next thing is I need combinations of two elements, and these are the most important ones. So I'd have to check A with B, and then B with A with C, and then C with A, and then B with C, and C with B. And so these are default cases that are obvious, but what about these? Are all three of these commutative? So if you pause the video and you tried to work those out, you will see that all three of them are. A operated with B and B operated with A, those are both equal to B. A and C and A, those are both equal to C. And B and C and B, wait a second. If we look at that, let's take a peek. If I do B with C, I get C. But if I do C with B, I get B. So it turns out that in this one, while this is equal to C, this one's equal to B. So those are not equal. And therefore, I could say this set is not commutative. So the set under this operation is not commutative. And we would basically take the same approach to show whether something is associative or not. So let's shrink this and do an associative problem really quick. So we're going to use the same set up there, which you can barely see, but hopefully you have in your notes. And what we'd like to do is we'd like to check some operations, all right? And for instance, I want to check B operated on B operated on C, and then I'd like to take B operated on B operated on C like this and see what I get. So if I go to the set again and I work this out, then here's B, here's C, so B operated on C is C. So I would actually end up here with a C here, and now I do B operated on C again, and that's C. So that's what this one is. So let's go B operated on B, and we can see that that is A. Alright, so this is A, and then I get A operated on C, and that is actually C. Do you see that in the diagram? A operated with C. And so I can say that the elements, or that these two statements, are actually equal, and therefore the two statements are associative. All right? However, is this set going to be associative, where under the operation little circle? And we don't know, and the only way we can check is to check every combination of associativity. And so there are a few more than we had on commutative because we're using 3 elements. And so I want you to think about that and then decide, would the whole set be associative? I'm not going to go through that example. There is a nice example in your book. Do they go through and decide if it's all associative? I don't think they ask you to do that anywhere in the book, but you're going to have to do all 3 elements, so you're going to have to give yourself a good shot at this one. So I was thinking maybe you can ask me in class if you can't figure out if it's associative or not, and we'll try that one in class if you want to see it, because it's a little bit longer, but I'll show you how to make the elements. So let's talk about identities and inverses. So how do we find the identity element? Well, what you have to check is you have to check what operated with A is going to give me A. And when I look at that, I see that A operated with A gives me A. And then the next question is, what do I operate with B to get B? So I'm looking, what goes with B to give B? And I see B operated with something here. So it looks like B operated with A, that's the correct element. And then finally, what do I operate with C to give me C? And once again, you should be able to see that is the element A. And so it looks like in all 3 cases, I use the element A, and when I operated it with A, B, and C, I ended up with the actual elements. So I would say A is identity. Alright. Now, to make sure it's the identity for the whole set, you have to check these in reverse. And so I got to check A and B, so if I go A and B, I still end up with B, and A and C, I still end up with C. And so that means A is the true identity for the whole set under the operation little circle. Okay? So A would be the identity. So what would be the inverse? How do you do the inverse? Well, the inverse is you take A and you operate with something, and what you want to end up with is A. And then B operated with something, you want to end up with the identity. So over here is always the identity of the set. And then C operated with something, I also want to end up with A. So when I look at this, I can see that A operated with A gives me A. I can see that B operated with B will give me A, and C operated with C gives me A. And so what I learn is this, that the inverse of A is A, the inverse of B is B, and the inverse of C is C. So you want to find the inverse for each element in the set. And that makes sense. For instance, in normal addition or subtraction, the inverse of 7 with addition is -7. And -7's inverse is 7. So they partner together in a special way and always stay together. So, just so you know, your assignment tonight is going to start on page 755. Not tonight, but tomorrow, 755. And it's going to be problems 24 through 64 even. Alright? So be ready for the quiz tomorrow.